So as power meter development has gotten more and more advanced, without this one piece of relatively simple, common technology found in basically everyone's home, sort of, you can't really drive power meter accuracy greater than like the 1990s claimed 2%, which was actually much worse. And what I'm talking about is an environmental chamber, just a simple box that can go to hot or cold temperatures. And a couple of years ago, when I needed something better than what I had currently been using, which was basically only an Arduino controlled oven, I needed to go cold. And I decided my time is really valuable right now, and if I can just throw $3,000 to $5,000 at it, this for a benchtop unit, I will do it in a heartbeat. And I couldn't do it. I couldn't find anything for less than nearly $10,000 for a benchtop model. So I guess we're building it. And well, I've honestly built this quite a while ago, but I've decided to kind of open up its most recently updated code and just kind of go through the design, because I couldn't find anyone on the web who's really, I'm sure there's a few people out there that have made an environmental chamber that can go hot and cold. Everyone have made reflow ovens and temperature chambers, high temperature chambers and stuff, but no one has really mixed the two. Now, there's some caveats with this, and there's going to be dealing with AC power, so your mileage may vary, all safety stuff. Yeah, like if you don't feel comfortable, don't do this. Just don't. But if you honestly keep to the cheapest, dumbest parts, you'll probably be okay. And yeah, so let's get into the basics of what is an environmental chamber. So simply put, an environmental chamber is just basically a nice insulated box, usually with a window. That's important to me. We'll come to that later. That can basically go to hot temperatures, basically an oven, and cold temperatures, basically a refrigerator or a freezer. So it can kind of be done in two ways. One of them is a reversible refrigeration cycle, commonly referred to as a heat pump. So you can do it via valves, or if you have a reversible compressor, it's just one side's the evaporator, one side's the condenser. You pump into the condenser. Yes, you pump to the condenser side, high pressure, loses heat and drops. Well, they're basically just two radiators and a choke between them with a compressor. So if the compressor can go either way, one side pumps heat into a chamber, one side can pump heat out. That's great for efficiency, but I'm going to do it the simpler way. We're going to have a compressor or a refrigeration cycle doing the refrigeration, and we're just going to use a dumb electric heater for doing the heating side. We're just going to try not to run them both at the same time, because that would be stupid. In my opinion, the refrigeration cycle, that's the hard part. I mean, it can be done with Peltier devices. I had a friend actually offer their device that they made for a local company while during work at home time that he built to replicate lab time. It works fine, but once you shut off the power to the Peltier device, it acts as basically a metal conductor to the outside world, and you lose a lot of your cool, or heat goes into your chamber very quickly. So you have to keep running it and applying power to it, but not too much power, and so I didn't like that. It also means building the whole box yourself. By buying effectively a wine cooler, or I could have done it with a refrigerator, but the wine coolers have a window because wine snobs like to look at their bottles of wine as they're cooling. They go, yes, I can see that wine is chilling. Yes, it does look like 5 degrees. At least that's how I envision wine drinking people. I don't really drink that much, so I haven't got a clue. So the actual refrigerator in question, I mean, that's kind of your starting point. I was lucky enough for 90 Canadian dollars to find this Medea wine cooler. Now, that's an interesting point. I wanted to be able to see what was going on. So my options are $4,000 smart refrigerator that has a hole in it, a camera, or wine cooler. I chose wine cooler. So wine cooler is ideal for that window side. However, the downside of a wine cooler is they don't need to get into really cold temperatures. So if you're like me, I figured room temperature, 25 degrees. If I can only go up to about 50 degrees because of the lithium batteries in the chamber. And well, maybe, you know, if I'm going up to plus 25, go down minus 25 from about room temperature, that's near zero. And wine coolers can do about zero. I actually got this one when it was brand new down to negative 10 with nothing in it, just running it flat out. But it's been a hard challenge to get it down near that again. And the reason is many smaller refrigerators and wine coolers use a refrigerant called R600. I only learned this recently from a website, YouTube channel called Hyperspace Pirate. And if you're a nerd about everything nerdy, he's doing some really interesting stuff with refrigeration cycles right now, but he's going cold, talk like negative 80 degrees Celsius. And what I learned is most of the refrigerants actually have a similar, I believe, pressure temperature curve, except for isobutane, which is R600, which is, when I say isobutane, yes, butane that's in lighter is same thing in a refrigeration cycle. Actually, modern stuff, one of the lowest ozone depleting and lowest greenhouse gas effect refrigerants, propane. So that's interesting. I actually don't know, and I've looked this up and I've searched it like 100 times, what the modern refrigerant is in refrigerators. I would know because we bought a refrigerator in November from KitchenAid, or from a dealer for KitchenAid, and it still hasn't arrived. We got we're still waiting 6 months later for a refrigerator. And when I get that, I will tell you what the modern refrigerant is. Or not, who cares? So R600, interesting, cheap, means the compressor is a bit on the weak side, which that's going to lead to some other fun things later. What you're looking for in a refrigerator is this little diagram that should be on the side, the back, maybe in a manual, probably not. I think there's regulations that they actually have to be on the refrigerator, but they can be a little bit dicey to find. You can see this one, thermostat, compressor. That's it, perfect. That's all we want. We don't want anything complicated in here. Multiple thermostats, multiple ways of interlocking things, lock out one temperature sensor into another. The big fancier the refrigerator, the more complicated this is going to get, makes it really hard. In our case, all we have is a thermostat that would exist here, which is gone because I did this again almost 2 years ago. So we have a thermostat, and that runs a little pipe. So this is the part that's electromechanical. That runs a little pipe back to a switch that has a pressure chamber type thing. So when it gets too hot, it expands, pushes a bistable switch closed. Because it's bistable, it basically acts as a mechanical bang controller. When it gets too warm, it comes on. When it gets too cold, it stops. So that is all well and good, but here's that kind of gotcha. One of the things I found recently when rewriting this is that you can get into a situation where your compressor won't spin. Why is that? Well, if you shut down the compressor after it's been running for a while, you have one side at high pressure, one side at low pressure, and you've been pumping all that fluid to the high pressure side. Well, now you have back pressure. So you stop the piston or spiral or scroll compressor, probably a cheap little piston thing, and now you're trying to start it, and you have that capacitor start that's going to pull a huge amount of current, and it just doesn't have the momentum, because normally when it was pumping, it would go, and every time it would slow down at some point, and then it could speed up, and it would store up that momentum. When you're just trying to start it, you can't. So in my code, you will find about a 5 4 or 5 minute delay. I can't remember which. And what I did was I tested on and off. I'd run the compressor for like 20 minutes and then I would stop it for so many seconds and run it again. And I found that 5 minutes is really safe. 3 minutes was pretty good. 2 almost worked. And for various different states of how long it had been running. So yours might need to have that number adjusted, but for these little mini wine coolers, 5 minutes is probably good. And that allows the pressure on both sides of the evaporator and condenser to even out through that throttling valve, and then the compressor can start. It's bad if the compressor is in this locked state because as I might have pointed out, locked rotor amps, it draws a lot more current when it's not spinning. It gets really inefficient and it just acts as a little heater that can eventually burn out your compressor. Now, this little PTC thing should safeguard against that. Don't know, who knows, don't risk it. So be safe. Give your compressor some time to cool down. I found when I was operating this in the summer in a non-air conditioned room here in the north, got up around 30 degrees. I actually ended up putting a fan on the compressor itself and on the sides, which is where the condenser is. The condenser, yeah. And that actually allowed me to keep things running much better. So not an issue now, but that hole that we now have from pulling out that thermostat that we didn't need, well, we can start running stuff back through that. But before we do, we pulled out that thermostat. We need to put something in line with it. We're going to put in an SSR. So that's just a solid state relay. Basically, it's a fancy triac sort of. We want it bigger than we really need for the locked rotor condition because we can still draw a lot of current, but these are common for like $15 on Amazon. And if you're lucky like me, there's going to be room in the back where you can actually just mount it down, keep it out of the way, and now you just have to run 2 small wires that can carry a 5-volt signal. So that's basically all of our cooling side figured out. We can control that with an Arduino. And it's just on, off. We don't need a PWM signal. We don't want a PWM signal, actually. We just really don't want it. It will ruin our compressor. But then it's just onto the heater. So onto the heater, I just got these 12-volt, 50-watt PTC ones. It's a small chamber. It's heavily insulated. I don't need it to rise heat too fast. And also, if it does, when I run it at full power, it takes a while for the chamber to circulate that air and for that thermocouple to warm up. But all the while, the heater is actually getting much, much hotter than the temperature that I want. So it's good to get one with a fan. That helps move the air around. I'm running that fan constantly. It's still controlled by a MOSFET, but no big deal. Maybe I'll add some smarts to it later. But right now, the code just turns it on. With the heater, though, we need a 12-volt supply that comes in and a heavy-duty MOSFET to switch it. We're doing low-side switching, so we can use an N-type MOSFET. You want one with a really, really, really low RDS on. Because otherwise, the first time I did this, it kept getting hotter and hotter and hotter. And so I think I'm down to 0.02 ohms, so 20 milliohms RDS on. You want one that'll also saturate pretty well, probably above around 3 volts, at the maximum 3 volts. So Arduino at 5 can definitely saturate it. Yeah, and so we can run that back to the Arduino. The fan's controlled through a FET, and the heater's controlled through another FET, and that heater one we want on the PWM. We also want pull down so that if we're doing a firmware update or it's just not powered, but there's 12 volts on the lines, that it's not going to run those FETs. It's just not. So pull downs are important. Doesn't really matter. 10K, fine. You can see I ghetto hack resistor surface mounts because I only seem to have surface mount resistors anymore. So Enclosure, yeah, I finally got off my butt and designed one and then 3D printed it, and then realized I used a bunch of filament on it, made a few mistakes, and I honestly don't really want to go back and reprint it, so I didn't. Did a couple of interesting things, like I made some slots inside so that I can put these magnets that I had left over in it, and that's great because, woo, you can't see it, but I'll show you. It basically can suck onto the side. Now, keep in mind, some of your wine coolers out there, if they're like mine, the condenser is actually on the top and or I think actually just the sides near the back. And that was weird, but okay, whatever. So it's a good thing I didn't drill a hole through the side. Also, good tidbit, don't try and drill holes in it if you don't have to, because you could have a stamped form condenser on the outside like mine, and frankly, you've ruined your refrigerator and lost a bunch of butane out in the world, which, again, low greenhouse and ozone depleting effect. Almost as good as propane, not quite, but still pretty good. So in the Enclosure, I updated the files a bit. The opening for the OLED, yeah, that one was a bit tricky. So hopefully I fixed that in the files. I think I did. But otherwise, I only broke 3 OLEDs, or 2 OLEDs, trying to put them in there and then cracking the edges, and they didn't work. So be careful of that. But currently, they're only showing temperature anyway, so who cares? There was a couple of gotcha points. If you follow the wiring diagram, you'll probably notice now that you can connect the 12-volt line from the power supply into the Arduino, and it does have switching between the mini or micro USB and the DC barrel jack, which I was soldering to. Honestly, don't do it. It worked fine until I was in a condition where the USB was plugged in, and then I turned on the power supply. I think it fires negative or too high positive. And anyway, whatever it did, it blew something out and blew up the Arduino. And I lost an Arduino. They're not expensive, but it's just one of those, you go, So there's that. Just don't do that, and you'll be fine. I also did a couple of don't be stupid things for those connectors. You'll see that I used 2 XT60 connectors, but one has one gender and one has another gender, and I don't know how we should be talking about the genders of our connectors now, but one's one and one's the other. And so in that case, I could theoretically take the one for the heater and plug it directly into the power supply. No harm, no done. But now I can't plug the power supply directly into the wrong side of the MOSFET, which harm would be done. I did sort of the same thing for the other side. So there's a 12-volt signal for the fan. Use the same connector as the signal, but the reverse gender for the signal to the SSR that controls the compressor. If I plug the fan into the SSR of the compressor, nothing will happen. You know, this is here me using the few ridges of my smooth brain. Basically, trying to make it idiot-proof so you can't plug the wrong thing into the wrong thing. I mean, except for that one time that's... Basically, I've been trying to make this idiot-proof so that you don't do something stupid. Plug a high-powered connector into this. You're dealing with both AC that you should be far away from if you kept your SSR near your compressor, which is good. But if you didn't, now you have AC near you. Same with the power supply. You have AC near you, but you also have 12 volts, and I'm currently using a overkill power supply that I think is 28 amps. That's not good. You can break a lot of your electronics with that much current. I guess the final thing is I decided to redo my code for this. Basically, I had a joystick interface and it wasn't great, and it depended on which mode that the code was set to for it to start off in, that it got dicey. So I made it work on SciPy. At least I think that's what they call it, SCPI, which stands for Super Can't Protocol Initiate. Silly Computer Pants Incorporated. I'll get this. Anyway, whatever it is, I can't be bothered to look it up before I do the editing. Should be on screen, hopefully. But it uses simple text-based languages. So you basically say NV, as in short for environmental chamber, NV heat, and then it will go into the heat mode. NV cool, it'll go into the cooling mode. And the difference between these two modes is in cooling mode, it can use a little bit, but not very much of the heater in case it overshoots into the cold. In the heater, it cannot use the compressor whatsoever. Otherwise, you might get into a condition where you're just doing this and wasting a lot of energy. So I didn't want to do that. I'd rather let the chamber just gracefully cool back down, and then eventually the integral term should take care of it. Those SciPy commands, they're in the code. They're very simple to use. Basically, you just say things like set the target temperatures. You can get the current temperature. You can get the current mode. You can set the mode with heat or cool. And you can tell it to run or stop. Fairly simple. Might add a few more things. I've left in the debug out when you actually run it, which unfortunately is 2 lines, but that's the default for that library. But it's mainly there as a, oh, it is running. Yeah, okay, it's not locked up. Other than that, honestly, I've used the environmental chamber for a bunch of my consulting projects now, and I just wanted to refine it now that I had some downtime because I'm actively not working on anything, to try and shore up some mental health stuff. So I still like sharing stuff. I think this is fun if you need an environmental chamber. So yeah, that's basically it. The code and I think the STLs for the 3D print is up there. You know, the wiring diagram in fritzing I made should be hopefully up there too. And you know, you got this video to see. It's very basic. It's basically connecting your Arduino to a few FETs, so you need to be able to know how to deal with your FETs. But other than that, like, just look for a simple refrigerator or wine cooler. My big thing is next I want to add some interior lighting that I can turn on and off remotely, and just to see what's going on. So previously I had tests in there and they had blinking LEDs to know that they're communicated, or that they were charging, or that they were discharging, or, you know, making sure things weren't weird. The racks have actually proved crazy useful. These stupid wine racks have proven useful for making mounts that I can hang stuff off of. And that's been pretty good. So hopefully if you need an environmental chamber out there, and you don't want to spend $8,000, $9,000, $15,000, or you're not Linus Tech Tips and you can spend $100,000 on a big one. Now keep in mind, this is not going to be nearly as fast. There's no humidity control, but I might add that later. But it's not going to be as fast to heat or cool. It cannot do sustained. You can't put a 200-watt computer inside this and run it sustained. This is more for your basic kind of lab tests. You're not trying to really push a machine. You're not trying to move that much heat. You just need to cool an area, and nothing in it is going to generate a lot of heat. Or you're trying to heat an area, and nothing else is still going to generate too much more heat. But yeah, I mean, about $200 to $300. You might get lucky and find a cheap wine cooler somewhere else, and you're off to the races. You know, you might have an Arduino kicking around. Other than that, hopefully you found this useful, and I begrudgingly say, I mean, if you did find it useful, maybe like, subscribe, comment. Apparently there was a revision in the YouTube algorithm recently that has now meant more subscribers are actually seeing my videos, and I've been trying to keep this up a little more. So yeah, a little all over the place between bikes and electronics, but I mean, that's basically my field. They've worked together for years. So with that, take care, and hopefully you learned something. And if you didn't, who cares?